In this video, we will be discussing the scientific method, as well as talking about how it was originally developed and some of the key terms in it. So the scientific approach to knowledge, also known as the scientific method, is a methodical approach to gaining new knowledge. It has its philosophical foundations in rationalism and empiricism, and relies on observation and experimentation to develop that new knowledge. It has a cyclic nature to it, which we will describe now. First, you start out with some sort of an observation of perhaps the natural world or a particular thing that you are looking at. That observation leads to the formation of questions. Typically, why did you observe the particular observation you made, or how did that come about? From that question, you develop a hypothesis. The hypothesis is essentially an explanation for your observation. Based on that hypothesis, you develop new experiments which you can test to see whether your particular explanation or hypothesis is correct. You take the data that you get from the experiment, analyze it to see if it is consistent with the hypothesis that you had or whether it is inconsistent. If it is inconsistent, then you need to make modification to your explanation of your original observation as well as the data you just collected to come up with a new explanation that covers both different objects or both different observations. You would then undergo the development of further experiments. You do your experimentation, collect the data, analyze it. If after analyzing your results you find that it is inconsistent with a hypothesis, you go back through the cycle and continue until you have an explanation that covers your original observation as well as all the different data that you have developed through the cyclic process. If you get to a point where your hypothesis explains not only the original observation but your new data, you then have an answer to your question. Over time, the accumulation of your data set as well as the hypothesis can eventually become scientific law and scientific theory. Scientific law is a summary of the results. It does not provide an explanation for why things happen. It just summarizes the observations. A scientific theory, on the other hand, is the explanation for what you are seeing. And as we will discuss in just a little bit, the term scientific theory is vastly different from scientific law as well as hypothesis. The development of the scientific method is often accredited to Francis Bacon, who lived in the late 15 and early 1600s. He is often cited as the founder of the modern scientific method. What this leaves out is all the work that paved the way for the scientific method. It's not as though it was an epiphany which developed on its own. Dating back to as early as 1600 BCE, you had Egyptian medical textbooks which utilizes the empirical methods using different experiments, which are a key component of the later development of our modern scientific method. Babylonian astronomy, roughly 600 years later, used mathematical descriptions for phenomena. So this was the first use of mathematical expressions to come up with explanations for phenomena. Greek philosophers then had added to this deductive reasoning and empiricism. Again, empiricism is one of the philosophical foundations of modern scientific method. You also had contribution from people like Muslim scientists in the middle to late 600s to the 1400 AD. Amongst these were Ibn al-Haytham, who developed the concept of scientific skepticism. He is well known for his work on lenses and spectroscopy. Al-Biruni developed the idea of repeat experimentation. Then you had Descartes in the late 15, early 1600s, who came up with rationalism, and then John Locke also further developed the earlier empiricism. All of these foundations led or enabled Francis Bacon to be able to develop the modern scientific method. It wasn't some Eurocentric idea. It had global reach in how it was developed. The foundational blocks to it stretch back to the 1600 BCE. Observations are the first step in the modern scientific method. They occur as the result of everyday experiences or through experiments. They form the basis of data that we use to make hypotheses. The data can be either quantitative or qualitative, and it is through the collection of those observations that we lead to the formation of our hypotheses or hypothesis if you're doing just one. The two people pictured in this painting are Marie and Antoine Lavoisier. Antoine Lavoisier is considered to be the founder or the father of modern chemistry. Marie, his wife, was instrumental in his work. She is accredited with translating much of his work from English and German into French, as well as a lot of the documentation, pictures, and sketches of the experimental setups that he did. If at any time while you are studying chemistry you get frustrated and think the person who invented it or came up with it should be dragged out into the street and shot, you should find solace in the fact that Antoine Lavoisier, who in addition to his work in chemistry was also a tax collector during the period right before the French Revolution, was actually dragged out to the street during the French Revolution and beheaded, mostly because he was a tax collector. As well as Marie's father, who had met Antoine Lavoisier through their profession of tax collection. The next step is to develop a hypothesis. A hypothesis is a tentative interpretation or explanation of your observation. For example, Lavoisier explained his observation of combustion by hypothesizing that when a substance burns, it combines with a component of air. The key to a good hypothesis is it needs to be falsifiable. So if we look at Lavoisier's idea that combustion involves the combination of a component of air with the substance that is burning, we can falsify that via trying a variety of different gases, those that are not air, seeing whether they burn, and then looking at individual components of air, combining that with the thing that we're trying to burn, and see how things burn or not burn. So for a good hypothesis, again, it needs to be falsifiable. The results of an experiment may support the hypothesis or prove it wrong, in which case we need to go back and either modify the hypothesis or discard it altogether. Scientific laws are a brief summary of an extensive number of past observations and have the ability to predict future ones. So, for example, the law of conservation of mass states that in a chemical reaction, matter is neither created nor destroyed. The key component to a scientific law is that it does not explain why things happen. So in our example of the law of conservation of mass, there is no explanation for why matter is neither created nor destroyed. It is just a summary of a large set of data, right? In all the experiments that have been done from Lavoisier all the way up until now, matter, the mass of our substance, if it's done carefully, is the same before a reaction and after a reaction. Now, one of the key components to a scientific law is that it allows you to predict future observations. So in the case of our law of conservation of mass, we can make the prediction that at the end of any chemical reaction, the mass of our products is going to be the same as our starting reactants, right? So when we're done with an experiment, it will weigh the same as when we started. With that, you are able to test the law via experiments. So if we do an experiment and we find that the mass is different when we're done than when we started, that would be something that shows that the law of conservation of mass didn't hold. However, typically if you're doing an experiment and you find something that violates one of the fundamental laws of physics or chemistry or biology, you should really go back and look at your experimental setup, make sure that you're accounting for everything. Unlike state laws, such as the speeding limit, scientific laws cannot be violated by choice. We cannot, by choice, have our products have more mass than our reactants. That it doesn't work like that. Again, the key component to scientific laws is that they do not explain why things happen. Instead, that is what a scientific theory does. So a scientific theory is the explanation for why things happen. There is a large difference between the term scientific theory and our everyday use of the word theory. Scientific theory is not our everyday use of theory. The everyday use of the term theory is actually closer to a hypothesis. So a scientific theory is the explanation for why a scientific law or set of observations occur. The difference between a scientific theory and a hypothesis is that the scientific theory encompasses a larger set of data and is more well-founded. So a well-established hypothesis or set of hypotheses can form the basis for a scientific theory. A scientific theory tries to explain not merely what nature does, but why a natural phenomenon happens. The theory itself explains both the characteristics and the behavior of nature. Some examples of scientific theories are Dalton's atomic theory and the Big Bang theory. These both contain explanations for a very large set of data. They explain why things happen. Theories themselves are validated by experimental results. They can be used to predict future observations, and they can be tested by experiments. Theories themselves can never be conclusively proven because new observations or experiments are always possible, which could reveal a flaw. One of the common misconceptions of a scientific theory is that it is stronger than a law. This is not the case. Theories do not become laws. Laws are the summary of a large set of data. Theories are the explanation for the data, right? The difference is why versus what. Theories are the why, laws are the what. They are different.